Hi, welcome to this week's ASAP seminar. I'm Sony. I'm happy to host today's session. Today we have two speakers, Yuxi and Konpat from Berkeley. And today they will be presenting the work called the serial scanning hypothesis. With that, I'll hand it over to you, please. Get started.
Thank you. Hello, everyone. My name is Konpat, and this is Yuxi sitting right next to me. Um, this work is also done with Kanana and Yutong. In this conversation, we'll try our best to give you the serial scaling hypothesis is. So let's get started. The plan for today with two parts. The first one is 30 minutes each presentation, and then we go after that with 30-minute QA, but also feel free to ask any burning questions anytime. All right. So what is a serial problem? Because it's super important to our thesis. So there's an old wisdom that women cannot make a baby in a month. What it really meant was human development is a serial problem. It's a serial process. You cannot paralyze and get it faster, right? So joke aside, for us ML people, we might be careless about what human development is, but we care about what reasoning, simulating dynamic systems, physics, video predictions, decision making, such as RL, right? So in one sentence, the serial scaling hypothesis says these problems need to scale more serial compute, not just the parallel ones. So this sounds very intuitive and reasonable enough, right? You know what? We don't quite follow these intuitions in the past. So let me give you a recap for such an example. So in 2017, we ditched RNN, which is perfectly serial model, to a transformer, which is parallel one. 21, scaling law, which we discovered, doesn't really make distinction between serial and parallel compute. And test time scaling, right? 2024, it doesn't really make distinction between serial and parallel compute again. So in short, flops are flops. There's no distinction between serial flops or parallel flops. Now, we are trying to use diffusion models to do visual reasoning, maybe unaware of the limitations of the diffusion models themselves. So what does serial scaling hypothesis do? First, it explains past success. Second, it connects to the complexity theory. And third, it connects to the practice. And to the at very end, we'll discuss about the implications of these three things. Okay, so first of all, it explains past successes. So deep learning is powerful because it is deep. I give you an example from Celia and Focus 2014 here. What it does show here is the AlexNet features. And basically it builds from the features, right? It's the edges to shapes to textures and to object components. By combining previous features and build the next one, it enables you to recognize any configurations of an object, such as a car with different colors, different bodies, different wheels, right? Imagine if you need to combine or could cram all this into a single layer of shallow learning. You need exponentially more many filters. So in LLMs, we also observe that chain of thought helps a lot, right? It gives better results. Why is that? Because it has more depth too, right? So it's also been a recurring theme in, I think, machine learning theory that the exponential depth width trade-off seems to be a thing. For certain functions, if you want to make it a bit shallower, you need to expand with much more width. So linear depth trade with exponential width in many, many cases. So the second part of this talk is it connects to the complexity theory. So in complexity theory, we know that there are problems that are not efficiently parallelizable. Well, those problems are called P complete. In this ring, outer ring of the P but outside TC, not known to be parallelizable, is one of the hardest in P. Because every P problem can be reduced to P complete problem. Another class of the problem is the TC, which we know how to parallelize well. Conceptually, you can think of that as problems that you can solve with neural networks with polylog in depth. So it's not because of lack of trying. For almost, I think, more than 40 years, we haven't found a single parallel solution to any P-complete problem. So it seems to be very hard to parallelize. So to us, it makes sense to draw a boundary between inherently zero problems and then inside the parallel problem. Okay? So to be clear here, there is no proof that P-complete is not parallelizable, but we do assume that they are not parallelizable. So another note here is we don't quite care about the NP-hard P space or some other hard problems outside. Why? Because the problems outside don't have the serial computation as their bottleneck. They're just hard. So serial or not, it doesn't really help. So put that aside. Now we can have a conclusion that P-complete is an inherently serial problem. And there are many good examples of these. First of all, math QA, right? Math question answering. Let me give you an example from GSM 8K, which is a relatively simple math benchmark. James spent 40 years teaching. His partner been teaching for 10 years less. How long is their combined experience, right? And you can write this as a graph, computation graph. 40 minus 10 is 30, plus 40, you get 70 years total. So this kind of problems is called the arithmetic circuit value problem, and is also P-complete. It's P-complete in the sense that it's serial in the depth of the graph. So math QA is a kind of P-complete, and there are also another types of problems called simulation problems. And two good examples are cellular automata and physics. And I give you a gist of that. So on the left is cellular automata. And for those who don't know, you start with the initial state at the top, right? Top row, and you follow a predefined 8 rules, which look very tiny local window. And then you put up the new row by row, okay? And the interesting thing is, with simple rules, there is no shortcut to go to the row number n. On the right-hand side, we have the physics simulations of just basically many balls colliding. It's simple to imagine how ball moves, but when it collides, you actually need to segment them into multiple segments and compute them one by one. In fact, you can simulate a Turing machine, which is two-dimensional balls colliding with walls, right? We call that a billiard ball machine. So it's definitely a serial problem. Okay, and clearly the video prediction is also serial because I just showed you in the previous slide the videos of those simulations, right? So basically video is kind of like an umbrella that can capture both of them. So what is the other problem that also relies on simulations? Is RL. More specifically, the policy and the value function are serial problems. Let me show you in the case of the value function. So in the most important problem in RL, that they need to be able to improve the policy is called the value function. And roughly speaking, it's a sum of the future rewards, right, of your current policy. So naturally, if you start from some state and following the trajectory, each step will give you one reward and one next step, right? And you need to go through this multiple times, but each time you need to ask, what is this action? So you need to go to policy. And what is the environment, right? So you do this multiple step until you reach your terminal state. So if the environment and policy is complex enough, this summation will have no shortcut, right? So in a sense, the value function is a zero problem. You just cannot do it without paying a lot of zero compute. So when model-free RL trying to approximate this value function V of S with a shallow neural network, most likely the approximated value is going to be biased. And if you have a biased value function, you will not get an optimal policy. So these problems we discussed in the paper in more detail, so feel free to check it out. But now, shift gear, we're gonna talk about how it connects to practice. So we have mentioned before, and it's also our collective experience that LMs did struggle like 1 or 2 years ago before we discover like chain of thought that they struggle with math problems. And people found that LLMs, like the transformer backbone of that, doesn't really know how to solve arithmetic, but they do solve with the bag of heuristics. And in theory, we also know that transformer has limited serial compute. And this also includes to the Mamba or other SSM models as well. So then if it lacks the serial compute, if we add more serial compute by chain of thought, it should work better, and it did, right? And also correspond to the fact that chain of thought genuinely gives you more serial compute. So a vivid example here, probably like cherry picked it, but this one came from Argaval and Willek, 2025. They did an ablation here. So this plot show you on the y-axis number of tokens and the x-axis number of tokens and the y-axis the average performance across math benchmarks. And if you scale in parallel, so basically you do majority voting, you get this curve, right? And if you do zero scaling, you get another one. So this shows the zero scaling that scale a bit better in math benchmark. Okay, so in RL, we kind of know that model-based RL is the one that give us the superhuman Go playing performance, right? In the AlphaGo, AlphaZero, and so on. And model-based RL is also have more serial compute than model-free RL, right? Because it gets you kind of like, it do MCTS, and it gets you further into the value function approximation. And in the locomotion, Kevin 2025 also showed that when you parameterize your value and policy networks with deeper models, you get bigger boost in terms of like time to go. Like, I guess this one is like standing or walking. If you do 16x the width of your network, you will not get as much as 2 times the depth of your network. So deeper networks is also more serial, so there's some correlations here. So I think at the QA section, this could be one question that might come up. I think it'll be fun to talk it through. Do you have any similar experience? Let's think together at the QA, right? So in terms of models, we compiled this nice table in the paper. We see that there are feed-forward models like MLP, transformers, SSM, and Mamba, which are parallel models. And then there are recurrent models, right? Like these four. But the story is a bit more complicated. We definitely know that RNNs, repeating layers, chain of thoughts are serial. That's already proven. But what we found in this paper is diffusion models is actually not a zero model. And let's discuss about that more. So apparently someone did to try to apply diffusion model to solve Sudoku, right? So you kind of add noise to certain digits and you hope that diffusion model will denoise to the correct Sudoku solution. But they sucked at it. And they also proposed a fix here. And you know how? They make it more autoregressive. So here, the author proposed that if you denoise in order, right, one digit at a time, in the order of the most confident digit first, you get so much better results, and it's measurable. So something is wrong with the diffusion model. they don't seem to scale well with more steps. And this has been reaffirmed by the literature, right? In Imagine, in depth estimation, in language modeling. So in this paper, Yuxi found that if a problem can be solved by a diffusion model, of course, with a kind of like limited depth backbone, with high probability, even with infinite steps, then the problem itself must be a parallel class TC0. And the ideal proof is not that complex. So let's take a look. So this is a setup here. We have a diffusion model with TC backbone. We need two parts. The first part is the problem statement. So we have some tokens define what the problem is, right? So that we know how to tell what is the problem to the diffusion model. And the second part here is the prediction. Hopefully, at the end of the denoise, you get the output. And this prediction, we have D dimensions. Okay, diffusion model, repeat this many times, right? For T steps. And then at the end, hopefully we get the predicted output. So this is the setup. And here's what the proof roughly says. So first, let's take a look at how fast does diffusion model approach solution to a problem of size n and output d dimensions. So we need two notations here. First, if we let this diffusion model denoise for infinite steps, it will give you the distribution of p infinity. And if we let it denoise for t steps, it will give you pt. All right. So this is how you measure the error, right? So the error between the t-step solution and infinite step solution is bounded by this big O, d over t, and t is number of denoising steps. This is a result from Li and Yan 2024. Tells you how fast the solution, like the diffusion model, converges to the solution. So for a close enough epsilon, right, the close enough acceptable error that is good enough to solve the problem, there is some complicated, more complicated details to define how you solve a problem. But you can put epsilon here and you get this big O. And if you do, you will look at a different perspective, right? It means that for any problem with output of d dimensions, you can solve within t steps. And this t is independent of the problem size. So diffusion model can solve any problem with d dimensions with a constant sampling steps, which means whatever that diffusion model solves cannot be a zero problem because it's independent of the end. So hopefully that is give you a gist of the proof, and there is a longer version in the paper. So the intuition here, why this proof works, is because the score function of diffusion model is inherently very smooth. So in like collective experience would tell you that it converges very quickly. Few steps, you get good images already, right? So when it converges very quickly, the underlying score function is very smooth. So that is the gist of the paper. Now let's talk about a bit of implications from what we learned, right? So what we learn is serial and parallel are completely different types of problems, right? And it requires different types of model to deal with. You cannot just say that the flops are flops because flops are not flops. There's serial flops and parallel flops. In this case, we still need a higher clock CPUs or GPUs if you like, but we need those because we cannot just hope that parallel compute will save us from serial problems. We also need new serial models and how to train them. We need recurrence. We probably need to reintroduce recurrence back into our models. And reintroducing recurrency into the model will make training harder. So we need a trick to deal with that. Third, this recognition of serial versus parallel might explain or partially explain why deep models are data hungry. This is more like a hypothetical, but I think is a nice thought. So let's imagine if you have a deep model, but it's not quite deep enough. So it has insufficient depth, right? And according to the exponential depth width trade-off, you need exponentially more width to deal with that problem because you don't have enough depth. And with exponentially more width, you have exponentially more weights. And exponentially more weights, you also need exponentially more data. Question mark. So if everything fails, you don't have budget, you don't have a CPU, you don't have better zero models, what you can do, I think, this is what I think. I read a quote from Polya, it's 1957. If you cannot solve the proposed problem, let's try to solve first some related problem. Hopefully that related problem is a bit simpler in terms of zero compute requirements and still give you some insights on what is the ultimate problem. For example, you can think of approximation of some zero problems could be potentially much easier, right? Or there's some good examples of how you change the problem altogether. For example, truncated RL. It's not going to give you any optimal policy because it's truncated. It only sees like, let's say, next 10, 20 steps. But in some problems, it's kind of good enough. And I also would like to beg you to take inspiration from the same math problems. So we know that factorization is very hard, and we tried that for thousands of years. But during trying to solve this problem, we also come with a lot of satellite problems, like primality. And we know that it's much easier. And we learned that because we want to solve the factorization. So I think with that, I'll conclude the talk. Thank you for listening, and I think we are ready for the QA session.
Yeah, thank you so much for the talk. If anyone have any question, please feel free to unmute yourself or just leave the question in the chat.
I'll check the chat.
I think one of the point that we can go to is this one. Oops, sorry. This one, right? That I posed earlier.
Yeah, that's the slide that you show at the end when you want to prompt questions.
Yeah. So have you experienced like any similar like this before?
So what he's trying to say is, have you seen situations that kind of look like your model isn't doing the task you want, but and perhaps that problem might come from you're trying to use a shallow model to solve a deep problem. Perhaps that is one reason.
Zero chat here. Great talk. Okay, thank you.
Well, that's not the question, but we'll take it. Or if nobody wants to ask a
Yeah,
question.
maybe I can ask one question. It's about just because that recently we try to maybe parallelize, for example, some loop transformer or some things, and theoretically that definitely the expressiveness has reduced. But I think a very challenging problem is that we have many synthetic tasks, some theories that we commonly use, like the Sudoku, some problem. But real world tasks, many of them are very knowledge intensive, so that you will find that you parallelize things or you just serialize two things that they achieve the same performance on real world task case. Yeah, for example, that I think that one huge challenge is that if we want to test maybe a very deep model, currently maybe the only very useful benchmark is the AGI2. In real world task, every time you will find maybe a transformer with no more than 100 layers is enough for all real world tasks.
Mhm. So do you want to recap the question again, Yuxi?
So, so you started the question by us talking about the loop transformer, but what?
Yeah, I just want to maybe the main question is how we can project the series the hypothesis into some real world cases in which applications should we really need them? Yeah.
So you're asking whether this actually is applicable to practical situations. Well, well, one of the inspirations is trying to explain chain of thought, really, because we believe that chain of thought constitutes some problems really helped by chain of thought, and in this framework, the reason chain of thought helps, at least one important reason, is that it allows you to scale, take a fixed depth model and just scale it up arbitrarily with, suppose you 10 times the chain of thought length, then that effectively gives you 10 times as deep a model. Well, it's not exactly the same as getting a model that is actually 10 times as deep, because basically in a chain of thought, the model has to output a discrete token from a small set of possible tokens. When to have a truly 10 times as deep model, it's like stacking 10 models on top of each other, such that each model can communicate a giant tensor across, but it's still better than a fixed depth model. So I think that's a fairly convincing demonstration that increasing depth really helps in practice.
I see. But I think that yeah, I agree this one, yeah, but I think the problem is about just I mean that even in maybe decoding step of the current transformers that you only convert the GM into a metric multiplication into a multiplication between matrix and vector. So I guess that we need some kind of maybe serious hardware, but maybe not so serious. Just I mean that at least on one dimension is still something paralyzed. Yeah.
What's the DMGM thing?
Just means that even the due chain of thought, the decoding step that you only decode one token. Yeah, but it only just means that it's a matrix multiplication between maybe one is maybe one times d, another is maybe still d times maybe the channel dimension, something like this. So I just want to say that it seems that it is not purely serial, just maybe series on one dimension. Yeah.
Yes, yeah. Yes, so you're saying something like in a transformer, you have giant matrix multiplications.
Yeah.
There's two way to scale the matrix multiplication sequence. You can make each matrix bigger, which is like using a longer input and wider width, or you can chain more matrix multiplications one after the another. That's basically scaling the depth of the transformer.
Yeah, that's right. Yeah, I think that this should be, yeah. I just thinking about because I think that building some serious hardware is very challenging. Yeah. So maybe previously that my hypothesis the best way is that maybe we should first parallelize them to make the full use of the hardware. After that, we do serial scaling, something like this. Yeah.
Oh, well, that's not the message we need to bring to the crowd. I'm sure NVIDIA is trying their best to do that part. We're trying to point out some other thing where maybe it's more neglected. Like, for example, standard CPUs, they run at like 4 gigahertz, but standard NVIDIA GPUs, they run at like 800 megahertz. So you can just multiply. I mean, I'm not a hardware engineer, but I imagine that it should be possible to multiply that by 5. And there are experimental CPUs that can run at 10 gigahertz. So there's like 10 times left to go, at least in terms of getting the processors to just run faster.
I see. Yeah, this makes sense.
I think there's another question in the chat.
Yeah.
So Andy Joe asks, for serial problems, I can try speculation to accelerate the process. This can still be benefit from parallelism.
Speculations to me means that
Speculation. I believe by speculation they mean something like speculative decoding.
I think so, yeah.
So speculative decoding. Well, first, speculative decoding goes as follows. Speculative decoding is a way to accelerate decoding from a causal transformer using the following trick, which is as follows. If you need to generate a sequence that is 10 tokens, then you need to run the decoding model 10 times forward. But if you want to check that if you already have a 10 token long sequence, and then you want to verify that this is what the model would have output if you output it, then you only need to run it once forward. That is basically how speculative decoding is supposed to save you compute. Now, how are you going to get the token sequence that you subsequently verify? Well, you usually use a cheap and dumber model to generate the token, and then you use the expensive big model to verify it once. But we believe, if generating the sequence to be verified is itself a hard problem, then you can't just bring up a cheap model and then expect it to generate that hard sequence effect efficiently. We expect that if you try to work it out, you will find that you need to run a cheap dump model exponentially many times, and that's another example of depth with exponential linear trade-off. So, but that would be an interesting direction to work out the theory. We have not worked this out in theory, but that's what we think is the most likely result of working this out in theory. Hope that answers your question. Now,
We have another one.
Kai Yue asked, do you believe chain of thought solve the serial computation problem completely, or do we need anything else? So now we can answer this question first in several ways. In the slightly sleight of hand theoretician's way, where we can just say that you can simulate a Turing machine with chain of thought, so you can solve any serial problem. But that's kind of boring and something that not satisfying even to most theoreticians. So we can try answering that in another way, which is, do we believe chain of thought solve the serial computation problem efficiently in practice or in theory? Well, in theory, there are some examples where chain of thought is less efficient than getting an actually deep model. There's this line of work called log transformers, which basically means like you get a transformer, but some layers in the middle, you can replicate them for more repeats before you output the answer. So some theoreticians, such as Merrill, have worked out the theory and found some problems for which log transformers can solve by repeating the intermediate layers for log many times. But to do a chain of thought, you need to do a chain of thought that is linearly long. So in that particular case, we have a kind of logarithmic depth versus linear chain of thought trade-off. Now, it would be interesting if we can find such phenomenon in practice, but so far, we don't see log transformers used in practice, so we don't quite know. But we think that log transformers are somewhat analogous to LSTM, or true recurrent neural networks. And so there should be examples that we can find in practice where a truly recurrent model solves the problem more efficiently than a kind of recurrent but not really model. For example, state space models, which they look recurrent, but they are not as recurrent as LSTM and RNN. So in summary, we think that chain of thought is not all we need, even though it's shown to be not all we need in theory, and it's possible that it also shows up in practice. And the place to look for is to see problems where LSTM is more efficient than SSM, for example.
Yuxi, wonderful talk. I'm actually part of a line of researchers that works on parallelizing nonlinear RNNs like GRUs and LSTMs. Are you familiar with that line of work or how it fits into the serial scaling hypothesis?
I mean, is it similar to trying to solve ordinary differential equations using parallel algorithm, for example?
It's very similar. It's all part of these fixed point techniques. So you're right that you could solve a.
I'm sorry.
It's the third order here. Anyway, sorry.
So sorry to interrupt you one more time.
No, not at all. Yes, it is absolutely related. Basically, like there's all these fixed point techniques that get used to parallelize stuff that seems sequential. So like parallel decoding, which y'all were talking about earlier, is kind of like Jacobi iterations. And then Andy Shi was parallelizing the diffusion model readouts using Picard iterations. And then myself and others like Lim et al. And Daniele et al. Use like these Newton iterations to parallelize GRUs and LSTMs.
I'm not quite aware of this line of work.
I mean, I'll just pretend that I am familiar, and yes, I will pretend that I'm familiar with the line of work and try my best. So yeah, and what's the question?
Well, I guess I was just curious how that plays into serial scaling hypothesis. And maybe the answer is just that when you have LSTMs or GRU, like we definitely can parallelize certain GRUs and LSTMs for application. And there's a really nice paper that just came out last month by Federico Daniele called Para-RNN, where they did it for language modeling. But maybe the point is that even if you have a GRU or LSTM that you can parallelize, maybe the point is that you could prove results saying that problem classes that LSTMs and GRUs can be trained to solve in parallel are somehow not truly parallel problems.
I mean, spiritually, that's the first answer we're going to give. Now, in more detail, even though we haven't looked into parallelizing RNN, we have, during the writing of the paper, looked into how parallelizable you can parallelize physics simulation, and that's how we came upon the parallel algorithm. So even though there's not much work done on the computational complexity of parallel in theory, we found some evidence in practice that parallel, it only works when the problem itself is smooth or nice. Basically things that are, for example, the diffusion modeling, it uses the heat equation, and heat equation is extremely nice, which allows you to backward diffuse very efficiently. And that is similar to how parallel works really well on problems that are already nice in that kind of way. And if the differential equation you're trying to solve is somehow stiff, then parallel doesn't work that well. Now, if we're going to guess what you will find if you look into the theory more deeply, then we will guess as follows. If you train an LSTM or hand design an LSTM such that it solves the inherently serial problem, then you will end up with an LSTM that is stiff in some linear algebraic way, such that if you try to parallelize it, you don't actually save time. That's what we guess.
I actually put out a paper where it was like we basically looked at the largest Lyapunov exponent of the dynamical system trying to parallelize, so like as a measure of stability, and we kind of found that the more unstable systems could be parallelized, the more stable ones could be. So it sounds like you came to the same conclusion just on the spot, which is very impressive. But thank you for your great points.
We can cite a paper.
Which one is this? Oh, hi.
Hello. I'll text it over. I'll put it in chat.
Wow, cool. Okay, so another question.
Felix Sartrin asks, doesn't the theoretical construction of log transformers contradict the serial scaling hypothesis? They are still parallelizable to some degree. I think that also relates to Deer elk parallel, and then which Xavier mentioned. Well, as we previously explained, the log transformers line of work, it doesn't really contradict for example, on what problems does log transformers really benefit? Well, let's compare three classes of models. We have fixed depth transformer, one forward pass. We have log depth transformer, one forward pass, and we have fixed depth transformer, chain of thought linear length. Mm-hmm. Now, in the log transformer line of work, they found problems for which a fixed depth one forward pass, it doesn't solve the problem, but you can either solve it with log transformer single pass or fixed depth linear forward passes. Now, that doesn't really contradict the serial scaling hypothesis. You still cannot solve the problem with a fixed depth single pass. You have to scale the serial computation in some way. Now, it does show a refinement in the hierarchy of seriality. At the lowest level, you have a fixed depth single forward pass that would be TC0 with I think I can't remember it right now, but I think the problems that require a log transformer that they constructed is in TC1, and it's also possible to get TC2 and so on. Even though I have looked very hard into the literature, it seems that no problem has been proven to be above TC2. It's like TC0, TC1, TC, and then you just jump directly to TC or P. It's kind of like that in computational complexity. I'm sure you kind of know it's like the fine structure of the computational class is very difficult to distinguish, but in short, that doesn't really contradict the serial scaling hypothesis. It refines it and shows some more fine structure in the seriality. Okay, I hope that answers your question.
Can I ask you a question about state tracking?
Okay, what kind of state tracking?
Yeah, I was looking at appendix B of your paper, and you have a point about how like if you're trying to like evaluate the S5 word problem, where we're just have a bunch of group elements and we're multiplying them together, you point out that you can basically do that with parallel associative scan, kind of like binary tree like approach. So that solves it in like log n steps. Like in your opinion, is that like serial or parallel? Because it's kind of like the same parallel trick that SSMs are using. What's your opinion on like where parallel associative scan fits into the mix? Is it serial or parallel, or what's the right way to think about it?
Yeah, like if we're going to put out serial scaling hypothesis version 2, I'm sure we'll try to figure out a word for those TC1 problems.
But is state tracking TC? I'm sorry that I just don't know really much at all about complexity theory. But is state tracking TC1 or?
I think in the appendix is your word problem, right?
Yes, yeah, exactly. Oh, I see. It literally says that. I'm so sorry.
So there are different kinds of state tracking, really. The kind of, for example, that the multiplying some a sequence. So the problem let me say that problem the problem is this. You have the permutation group on 5 elements, and you give a sequence of elements from that permutation group, and you ask, if you multiply these elements in a sequence, what would the outcome be? Now, as you said, you can just do the binary tree multiplication and solve it in log serial steps. That is not a very difficult kind of state tracking if you think about it. It's more difficult than, for example, multiplying elements in a group on a hypercube. That is even more parallel. That is I think that one is in TC0. Now, multiplying elements in a group is in general TC1 because you can do the binary tree multiplication algorithm. But that is pretty simple. That is pretty simple compared to general P problems for which you have a kind of arbitrary dependency between previous and next. Every step has to follow each other because in group multiplication, groups are very good. In group multiplication, groups are associative. Associativity really helps here, but in general, you don't really have that associative structures. So I think that's where the key lies between the TC1 class and P completeness class. So intuitively, I would say as follows. If you can do 3 kinds of state tracking. There's the really easy kind in TC0. There's a little harder, but still group-like kind of state tracking where you have associativity. That should be in TC1. And finally, there's the arbitrary serial dependence, which is like evaluating the Boolean circuit value, that should be in the full P class.
That was really helpful. Thank you so much.
Yeah, I think there's another one point I want to add regarding the Valerie associative scan, why MAMPA cannot solve it. So in the William Mirror's paper, that paper already show like if you have a linear recurrence with a dense transition matrix, that is sufficient to solve S5 problem. Yeah, and this could be for arbitrary linear recurrence. You can definitely use the parallel scan to calculate the recurrence in a parallel manner. I think the issue of MAMPA is related to the state transition matrix itself, because it just uses a very simple diagonal transition matrix, and this one is not sufficient to solve this task. For some other linear recurrent model like delta night, delta product, for example, if you use 4 household product as the transition matrix, I think that one should be sufficient to solve the S5 problem.
So can I actually ask, or like to anyone who wants to answer, but would it be enough to take the Mamba transition matrices and just make them complex valued? Kind of like it just basically turn Mamba into complex parameterization so that they're kind of like dense matrices with the change of basis, or
I think if you only change it to a complex value, it basically is like converting a diagonal transition matrix to a block diagonal transition matrix where the block size equals to 2. And this is a highly structured, it's mostly diagonal matrix, right? It's just like the block size equals to 2. I don't think it changed much regarding the expressivity. So in this sense, I think like there's a paper in the open review member 3. They use this complex value transition matrix, and I believe member 3 is within the class of TC0. You cannot solve the state tracking this S5 task by itself. Yeah, they didn't report any result regarding the S5 word problem. They only show some interesting parity tracking result, but that problem itself is within the class of TC0.
that makes a lot of sense. Thanks, Solomon.
That would be an interesting literature. Can you put the link in the chat?
I can put the link.
Thank you.
So there's a paper called Delta Product. So basically, you can to solve this S5 word problem, you can have a linear recurrence. The transition matrix just need to be a household matrix product, and household matrix is a reflector matrix. It can model this kind of permutation, and if you have enough number of household matrix product, you can model arbitrary this kind of like permutation, stuff like that.
Yeah, we'll check it out. Thanks for kind of answering questions in our Q&A session.
Yeah.
That's great. That's
The
great.
what you're looking for is just thank you.
Yeah, I have another question. So, since both trail thought and increasing the total number of depths are 2 different ways to increase the total number of like serial computation, so which one do you think is more practical to solve really hard real world problem? I think there are some theoretical results by William Merrill, and there's a paper called "A Little Depth Goes Further," and that paper arguing, okay, if you do the scaling in the depth dimension, for example, those loopy transformer, universal transformer, yeah, that serial computation is way more effective than train of thought-ish a horizontal serial computation. I'm curious about your thought, and yeah, and also there's also a recent relevant paper by ByteDance. They scale up a universal transformer-ish model to a very large scale. Yeah, and go trying to find the paper.
What was the very large transformer you mentioned?
Let me share the paper in the chat. Recently,
that's-
there's a paper by ByteDance called
Hmm.
Scaling Reasoning Well-Looped Language Models.
That's very recent.
Yeah, very recent. Yeah. I think this one is like the first very large scale open source universal transformer-ish scaling in the vertical dimension. Yeah,
Amazing.
I think this recurrent depth approach makes a lot of sense for doing this serial computation from the theoretical perspective. Then train of thought. Do you think this kind of approach could totally like replace the train of thought approach in the future?
Now, so you asked two questions. The first question asks whether the first question brings up the Mario paper, a little depth goes a long way, which shows in theory
Yeah.
that the log depth universal transformer solves a problem that requires linear chain of thought to solve. Yes, that we previously mentioned as a kind of refining the hierarchy, refining the hierarchy of seriality. They showed some problems are in TC1 class which can be solved with log depth, but linear chain of thought. Now, whether such problems appear in practical situations, well, it's possible. And where we might look for their appearance would be to look for problems where you are tracking states and you have associativity such that you can do the binary tree multiplication kind of algorithm. Now, we haven't looked into that in the paper, but we might look into that in a future paper, and you're also encouraged to look into that. It is quite possible that such phenomena do occur in real life. It's just that people haven't noticed it yet because they don't know what to look for. Now, the second question you asked is about whether such kind of looped language models might replace chain of thought. Now, if we are just trying to, okay, so we can answer that first in the most theoretical way, which is that anything that you can do with a chain of thought is theoretically possible to just do it in a loop, because you just do the chain of thought inside the loop and then you output the final answer without showing the intermediate steps as output. So in theory, loop transformers have at least as much computational power as chain of thought. So that's pretty obvious. Now, more interesting question would be, in practice, how you are going to find such a looped transformer. So at least right now there's a kind of inertia wherein training a transformer with constant depth and doing chain of thought, you have already years of data that you can just train the transformer on. Whereas it is not obvious that you can just get a looped transformer to internally produce something similar. So basically it's like if you want to train a fixed depth transformer with that uses chain of thought, you have all those teacher reference trajectories you can train it on. So, but the loop transformer, it kind of has to do it from scratch. It has to think up the intermediate steps on its own, kind of.
So
So
I
in
have
terms
a
of that,
I
yes.
have a quick question. So are you saying like for train of thought, you can use a very large teacher model to materialize the train of thought token and use that token to teach a smaller model to think?
Oh no, it's something simpler. It's simply the fact that the internet is already full of chain of thought examples. So you can just grab it and train a chain transformer to do it. So we expect that at least for the short term, there will be technological inertia, whereby people will keep training fixed depth transformers because there's all those good data to train it on. Whereas if you want to train a universal transformer, the universal transformer kind of have to itself think up intermediate steps because you can't just grab internal chain of thought from the internet. There isn't any for now. So, but if universal transformers really do work better in practice, then that will be a temporary technological inertia that should be overcome in a few years.
Did you see the hierarchical reasoning models? I think they used some RL tricks to supervise even the looped intermediate representations of the loop transformer. I think that's pretty cool.
I mean, the paper looks cool, but
Have you read it?
I have not.
Come on, can you pull up?
Yeah, I did read that paper.
Great. You have read the paper.
Oh, okay. So I find it super cool. I agree. And the trick is they use like the implicit gradient with like fixed point, right? To train very deep recurrent. I think like something like transformer.
But then on top they did like a deep supervision thing. I didn't fully understand it, but they had like even additionally to the implicit thing, they had another outer loop where they kind of had even the targets from the prediction like supervised deep into the loop with some adaptive computes, reinforcement learning, policy stuff. I'm not sure.
There are many layers of that paper, right? To my understanding, the coolest part is the fact that they can train without like backprop through the whole chain of recurrent repeating layers of network, right? And they construct a layer such that it will kind of like converge to a fixed point, and with some gradient trick you can backprop without actually backpropping through it. And then they repeating this block many times, and they say that each time you repeat it, you have like deep supervision, as you mentioned. And then you also have a question of how many times you want to repeat that block. And that's where the adaptive computations comes in. It's not easy to train a network to say, okay, I will run for 3 steps or 4 steps, right? That's kind of like this like discrete decision making. So they use RL to supervise that. So there are many layers on top of that, but the serial part is like, I think the innovation of training this is how you think of training a deep network without spending the cost of backpropping through the whole potentially very complex network.
Yeah, I think you should also look at maybe the tiny recursive model if you haven't yet. These things, I think there's a few new ideas in these papers that go beyond just the implicit differentiation trick, and I think it's quite exciting to see this.
Definitely. If you can put the link in the chat as well, so people can take a look.
Sure.
These are cool papers. I would love to read. Thank you. You found it?
Yes.
The tiny recursive network.
I found it for you. You don't need to look. Kaya has another question. Is it really true that loop transformer is at least as expressive as COT, looping only for log n steps, looping for not as the well, well, nobody said that you only need to loop for log n steps. You can, of course, loop for n steps, and if you loop for n steps, then you can, of course, reproduce a length n chain of thought. After all, in chain of thought, each output token is only chosen from a very small set of like 40,000 discrete points. Whereas in a loop transformer, each forward pass of the loop outputs a big tensor that is like, let's say, 1,000 dimensional real 1,000 real dimensions. So there's definitely a lot more space for reasoning in a loop transformer than in a fixed depth transformer chain of thought.
Is the comparison here actually fair? Like, because in COT, if you actually like generate n tokens, you do not only like generate this n tokens, you also like produce the KV cache for the like a new n KV cache for like the new tokens. So in terms of, I think if you compare spaces, I still don't see why, like, at least theoretically, like if you don't consider the actual like empirical calculation, if you only consider theoretically, I think it's almost apparent that like loop transformer, even if you loop for like poly n time, cannot solve any problem that requires n square space if your width does not grow like linearly with the context length.
Oh wait, do loop transformers, hold up.
Yeah,
Hmm.
I think
Okay.
I think what Carrie wants to say is like the additional KV cache brought by COT increase the space complexity, and for some problem, the space complexity is really crucial. And the universal transformer, loop transformer, they do not have maybe they do not have enough scratch pad to do the intermediate computation.
Okay, that's a very yes, space is more powerful than time. At least that's the folklore of computational complexity theory. So from that perspective, perhaps you could do more with chain of thought than with loop transformer if you are trying to solve some problem that really requires a lot of space. In practice, that might take a while. So unfortunately, I'm not familiar with the space complexity theory. We kind of regulated it into the too difficult to handle case because P space is extremely big, way bigger than P, which is why we haven't looked deep into this. But theoretically, it might be one part where chain of thought is better than loop transformer. But if that's the case, that is a little bit of an incidental feature. And there's no reason why you can't just give a loop transformer more working space, more scratch pad in the middle, and recapture the power of increasing space.
I see. Yeah, that makes sense. Thank you.
Yeah, I just wonder, just mentioned Scratchpad. So basically, if we add a third component or a third variant, which is storage or memory, how would it affect the whole trade-off between parallel and sequential?
What is the third component again?
Space.
Memory, storage, basically, right? Like universal storage, not just, TV cache or Scratchpad, but completely addressable storage, unlimited.
Like rack style storage?
Like Turing machine storage, whatever, I don't know.
You mean
You have two axes right now, either parallel or sequential, right? But
Yes.
now, what if you add a third axis, which is like you could store any intermediate result and retrieve it later? What would change in this dichotomy between parallel and sequential? Like in general consideration, I just wonder.
Well, in complexity theory, there's the kind of space and time trade-off which we did not investigate in the paper because we kind of regulated problems that really require increasing amount of space as too difficult to handle, since it is known that P space is extremely hard. At least problems that are really in P space are extremely hard. So we kind of just regulated it as outside of what we are trying to solve, because those questions are things that serial computation isn't going to be the critical factor between solving it and not solving it.
So is there an intuition to be had here? If you give a model more space, is there like intuition that it tends to solve problem more efficiently, or no? We don't have that.
I can't generate an intuition right now because I haven't thought deeply about this.
That's fine. That's fine. I think better not to be wrong. There's another question, I think.
Okay, hold up.
Can't see anything.
Could discrete, okay, Shu-Ming Hu asked, could discrete reasoning tokens as in COT help with generalization where reasoning in latent space could overfit more easily? Discrete reasoning.
I guess that's it. Like the question of chain of thought is always like one of the like 40K possibilities,
Yes.
but like continuous space is more larger.
Well, the way I would kind of reverse the argument is basically, well, can't we go even further? Instead of imposing chain of thought every 96 layers, we require every layer of the model to internally add, so that even inside the model, the layers still need to communicate in discrete tokens rather than in big tensor matrices. Well, deep learning still works. So if the training procedure is good, then perhaps a looping transformer should not be bothered by overfitting any more than previously working recurrent models such as LSTMs. LSTMs can run for thousands of steps without going off the rails. And I think there were also some crazy work that tried to scale to 10,000 layers. I don't think people actually did anything with it, but apparently it could be done. So yeah, I think the problem of overfitting is a technical issue related to training, and that is solvable. So that's how I'll answer it for now.
You.
Okay, we have a lot of discussions. I think we better. It seems that we do not have further question, and let's wrap it here. And thank you again for the amazing presentation. And I also very enjoy this discussion. Yeah.
Thank you, Celine, for inviting our grad student. I think they definitely need to practice the talk. It's a very cool workshop. Thank you.
Yeah, thank you. I'll stop recording.